We now look at how to negate a universal conditional statement. First of all, we already know that the negation of the universal statement is going to be a existential statement, and we have two parts, right? So in other words, applying the previous result, we're going to, the negation of this universal statement will be an existential statement. There's exists X in U such that, and then we should negate this guy. So we're going to negate P of X implies Q of X, right? And if you recall that, what's the equivalent form of P of X implies Q of X? It is actually, this guy is equivalent to not P of X or Q of X. Just give you one quick refresher. Like if you don't freeze or I will shoot, right? So if you don't freeze, then I will shoot. So that usually I use a phrase to help you remember this relationship will be the trick that I advise students to do. So these two are equivalent. So therefore, how do we negate this guy? We're going to negate that guy using the De Morgan's rule. So therefore, this is equivalent to the exists X in U such that, okay, the negation of that is going to be not P of X, which means P of X. Negation, apply the De Morgan's law, this becomes N, and then not Q of X. Right, so that's how we negate a universal conditional statement. And let's apply it. For all students P, if P is taking calculus 2, then P has already taken calculus 1. So according to this result, we know the negation will be the exist students P, right? Students P such that, and now the P, the first predicate. So this is the first predicate. This is the second predicate. So we'll keep the first predicate, which is P is taking calc 2 and negates the second one and negates this guy. P has not taken calc 1. P has not taken calc 1. So that's the negation of this universal conditional statement. And so I hope that you do appreciate how nice the formula is, how we derive that. That's really a neat way to we can precisely negate a universal conditional statement now without much trouble. Take a look at the second one. If a student T is not in class today, then T is sick, right? So basically this one, you can imagine this is actually for all students. This is a kind of a little implicit that we can add a for all students. If a student T is not in class today, then T is sick. So to negate it, we're going to say there exists a student T such that this is the first predicate. This is the second one. So such that a student T is not in class today. And then you're going to use N, and T is not sick. So that's how we negate it. Some other variation of the universal conditional statement, the variant. So for all x in D, if P then Q, let's write its contrapositive. Let's quickly review that. It's going to be for all x in D. It's contrapositive. We have to negate both and swap them, right? So not Q of x implies not P of x. The converse, we have to make conversation. So switch them, kind of like making conversation. When P talks to Q, then it's Q's turn to talk to P. So Q, yes, Q of x implies P of x. The inverse will be negating both and then keep the order as not Q of x. So quick review on those invariants. Now, another thing that we want to also review is like sufficient and necessary condition. So we earlier we introduced P implies Q. This is called sufficient condition, and this is called the condition. I'm sorry, necessary condition. The necessary condition for P. This is sufficient condition for Q. Now, let's rewrite the following into the form of universal conditional statement. For all x is a sufficient condition. Therefore, because it's sufficient, therefore it has to go to the front, right? The front one is the sufficient. So therefore, I know for all of x implies S of x. Because R is sufficient, it goes to the front. Now, if you say for all x is a necessary, so because this guy is a necessary, it has to go to the back now. So therefore, this one will be for all x, S of x implies R of x. Now for the only if, Rx only if S of x, that means if there's no S of x, then R of x won't happen. Not S of x, then not R of x. So this is basically, if there's no S of x, then you would not see R of x. This is equivalent to say R of x implies S of x, right? So basically for all x, R of x implies S of x. Okay, now let's wrap up this particular section by attempting these two problems. So I hope that you will begin to appreciate how nice the kind of the predicates calculus that we have been studying can help us to rewrite a statement correctly through these couple of examples. Take a look at the full attendance is not a sufficient condition for getting an A. Okay, again, I would strongly encourage everyone, pause the video and then give a try yourself to see if you're able to rewrite this statement without using the word sufficient, okay? All right, so here's what I would do. By the way, to save a little time, I'm gonna say, suppose I would use F to represent a student having a full attendance, and let A represent the statement for a student getting an A. So now, F is not a sufficient condition for A. That means it is not the case, right? It is not the case that F is a sufficient condition for getting an A, okay? Well, I'm gonna move this down a little so that I can work on here. Okay, so this is what it means. Now, and we just reviewed that when it says a sufficient condition, that means it has to go to the front. That means F is in a conditional statement. This guy means F, full attendance implies getting an A. Okay, of course, the original statement is equivalent to, it is not the case. Full attendance implies getting an A. Well, again, how do we negate that? If you remember, this F implies A is the same as not F or A. Now we are gonna apply the De Morgan's rule. So F and not A, right? Now we can rewrite this symbolic form into English. That means we see a student who is getting a full attendance. So there is a student who has full attendance and or but either way, but not getting an A. Getting an A. So did you get yours correct? Correct. So this is what it's supposed to be when it. Oops, I'll just keep it here. So this is how we rewrite this statement without using sufficient and condition. So this is much more, much easier to understand for a student who has not taken a discrete math and comparing to that one. Now let's try the next one. Full attendance is not a necessary condition. So not a necessary condition. So I need a little space. Maybe I'll just write it on the right side. Okay. So this is the same as saying it's not the case that full attendance is necessary condition for getting an A, right? So this is what it means. And because F is a necessary condition, that means it has to go to the back. So that means getting an A implies F. So necessary goes to the back. Now again, repeat what we just did. This is equivalent to not A or F, and which means the negation is A and not F. Now this is saying there is a student who is getting an A, but or and not having a full attendance. Right? So just imagine without going through that, it might be very challenging to rewrite this into this statement and rewrite this into this statement. I hope everyone appreciates the discrete math more through these two examples.